Lane's balance and the concept of the graded river are two of the most important and central concepts that we have in fluvial geomorphology, so the study of rivers and their form and the processes that shape them. These concepts help us understand what sets the slope of a river channel and whether that slope might change over time because of excess sediment coming in, perhaps piling up, or excess water coming in and perhaps sweeping that sediment away. These are processes that are dynamic in the landscape, and so in this first picture, taken in southwestern Argentina outside the town of El Chaltán by the iconic Peak of Fitzroy, we can see the river flowing in front of us, and as I move the mouse here, you can see that there are a couple bars formed of sediment, right? And this is sediment that came in from the mountains, from higher up in the catchment, that the river is flowing from left to right across this map, or across this photo rather, and that's from west to east. And if it's flowing in that direction, then the west side must be higher than the east side. It's flowing predominantly under its own weight, under gravity. And so what we want to understand as fluvial geomorphologists is what sets the slope at which it flows, and how that flow and potentially flow resistance related to sediment might be driven by larger scale hydrologic and geological geomorphic processes existing at the catchment scale. And we don't have to look a whole lot farther on the landscape to see why these processes and considering them is important. So just off the side of this river, you see these really flat surfaces over here. So there's one here, and then there's another one up there. Those are called river terraces. Those are ancient preserved river floodplains from times in the past at which the river was higher. Over here is the modern floodplain. And so you can imagine that if you had a way of geologically dating these different floodplains, or preserved ancient floodplains called terraces, you might actually see the evolution of the river through time as it cuts down into the landscape and be able to understand the rate at which that happens. And that's something that can be useful for knowing rates of landscape change, or seeing if the rivers are keeping pace with tectonic uplift and how quickly they're incising. So are they able to cut down into the landscape as quickly as the rocks are being uplifted? And they can also be an important benchmark to compare against modern day change. And so today, in many parts of the world, humans are such dominant drivers of landscape change and landscape evolution that we might start to wonder, are we moving substantially more sediment, more material across the Earth's surface than nature would? And those sorts of questions we can answer by finding out how quickly natural processes operate in the absence of significant human impacts by dating these ancient features. So we're going to put all of that ancient side of geomorphology aside for the moment and focus just on these rivers and what sets their slopes. So first off, we're talking about graded rivers, and we might wonder what's in a word. So the word grade is used often to indicate slope, and it's often slope with a percent sign associated with it. So grade just means slope, and so you might have something like in the lower left, that's an extreme example of a steep slope, so 16% grade, and that's taken from this YouTube video of a teacher talking about slope and driving down into the Columbia River Valley, and probably in Washington, maybe in Idaho. And we have similar signs here in Minnesota if you're driving into the Lake Superior Basin, for example, and suddenly dropping off the edge of the uplands, or if you're driving down into the upper Mississippi River Valley or the Minnesota River Valley. When we talk about rivers, we are talking about the slope down channel, so the downstream distance. And so this example here has a couple stadia rods, and those rods are being used to survey the slope of the river surface. And so you can imagine that the upstream side is higher than the downstream side, and with most rivers, the water surface is approximately parallel to the bed surface. I wanted to show you a few examples before we get too far ahead, just so you have some pictures in your mind of what rivers with different slopes might look like. So this is Clear Creek. It's west of Golden, Colorado in the US, and its slope gets up to 6%. And so 6% might sound like a small number, right? Like if you get 6% on an exam, you're not doing so well. But 6% grade for a river is just really, really ripping. And so if you imagine that you're trying to paddle a river, it is dropping 6 meters out of every 100. So every meter that you go downstream is dropping 6 centimeters. That's a pretty steep slope. You can imagine if you're on your bike, a 6% slope, you're going to be accelerating very rapidly. And if a 6% slope continues for long enough, either you're going to reach terminal velocity, in which case the wind is pushing you back as quickly as you're going, or you're going to be a scaredy cat / a wise person and hit your brakes. So this river has a gravel and boulder bed. And just to kind of give you a bit of context, you can see that path on the left-hand side of the river. So it goes into being a footpath, but the part that's closer to the viewer over here is probably approximately big enough to park a car. And so you can see that these are sort of like small car, like maybe smart car size blocks sitting in the river. And these have probably been tumbled down from the hill slopes on the side. We can talk at some point later on about how hill slopes and channels interact and how they exchange sediment and how landscapes evolve. Right now, focusing on the river, this deep river is capable of moving these gigantic blocks that you can see tossed around in it during its floods. And so this 6% slope, really coarse sediment in it, and you can imagine then that this river, which is a fairly small creek, quite a nice one though, is adjusted to, with its supply of water, be able to move these really big rocks. And as a result, it needs a really steep slope. And so it has carved a valley to this right slope to move these rocks with the available water supply. All right, let's move this down a little bit. So here's the Cannon River. This is the Lower Cannon in Minnesota. And you can see over here on river left, and so we call the left side of the river river left when you're looking downstream. So on river left, you can see this gravel bar, and these gravels look like they're maybe, like 10, 15, 20 centimeters. So a lot smaller than the big rocks that we saw in Clear Creek. And likewise, the grade of the Cannon River is about 0.5%. So the slope would be 0.005. And so what we have here then is a classic example of a gravel bed river in nature. And these are some of the most common rivers that we see around the world, together with what we'll see next, which is the sandbed river. And so for this, I'm taking the example of the Minnesota River. And so the Minnesota River is a really extremely low gradient river. It has a grade of 0.02% approximately. I got that from just a quick look at Google Earth elevations and tracing a path down the river. So that might not be totally scientific, but it's going to be in the ballpark. Right? And it's close enough for you guys to get the idea that this is a very low gradient stream, and its bed is made of sand. So this river can't move gravel, it moves sand instead, and therefore the slope that's required to move the supplied sediment is very, very low. So this all ties in with the concept of the graded river, and I don't often go back into old literature, but this is just such a classic and really well explained concept in this paper by J. Hoover Mackin that I'm actually going to just read the sentence. And so I pulled this out of, I believe, the second paragraph of his paper, and he wrote, "A graded stream is one in which, let me start again. A graded stream is one in which, over a period of years, slope is delicately adjusted to provide, with available discharge and the prevailing channel characteristics, just the velocity required for transportation of all the load, or of all of the load supplied from above." So that's a lot of commas. But the idea here is that there's a balance in which the slope will change in order to allow the stream to move the material that's supplied. So in here, grade is therefore indicating an equilibrium state Or what we talked about earlier in the semester, a steady state, right? So I talked about steady state, meaning that there were no time derivatives, there is no variance in time. And so here, if the same amount of stuff is going out as is coming in, then the channel bed elevation is not changing. There's no deposition and no erosion. We might think about why this is or how we reach the equilibrium state, and that's where we get to Lane's balance. So that's a couple slides down the road. Or actually the next slide. So Lane's balance here is interesting. I had somehow thought that I had changed these slides a little bit, but I hadn't. Well, anyway, so Lane's balance here is telling us the balance between aggradation or sediment supply to the channel. All right, folks, I just paused it and removed the offending slide that tripped me up. So I had changed these slides a little bit, and I had forgotten to delete one. So here we go. Bear with me. In the future, I might edit this all out, but it's 2020, and we're just going to keep on pressing on. So what Lane's balance is this conceptual model for whether a river is going to aggrade or build up its bed, or in size, or erode through its deposits and cut downwards. And so aggradation and incision are two important words. And so what you can see is that on the left, there's sediment in this balance. And on the right, there's water, represented by this little kind of like Kool-Aid man jug with a fish in it. And the idea here is that if there's more water added, for example, this is going to get heavier on this side. And then the stream is going, and so this side is going to go down, this side will go up, and this needle will go this way. And this is going to cause what's called degradation, which is the same thing as incision over here. So, and on the other hand, if we add more sediment, that's going to cause aggradation. We also have sediment size up here and stream slope up here. I'm not going to focus so much on the grain size of the sediment, though you could see some conceptual, hints of steep rivers are associated with large sediment. But let's look at the slope here. So if I make the stream a lot steeper, then this water has a lot more leverage, has a lot more ability to move sediment. And so for a very steep stream, I can be in steady state in the graded river, so at this 0 point, with less water compared to how much sediment I have. And likewise, if I have a very gentle stream, then I need a lot more water compared to sediment to be able to transport that sediment. And the stream, in fact, will naturally approach the state of balance. Because if there's a stream that has more water than is needed to transport the available sediment, that water will start picking up sediment from the bed and will cause the river to incise. But as it picks up that sediment from the bed and removes it, it's causing the river to cut down, and therefore is eventually lowering the slope of the bed of the channel. And so we're assuming here that these rivers are always grading to the exact same base level, so the exact same final elevation. So if there's any erosion and you can't change the position of the mouth of the river, any erosion is just going to cause the river to decrease in slope and is eventually going to bring it back to an equilibrium state of the graded river. And likewise, if there is deposition, so let's say that there's a whole big pulse of sediment being added into the rivers, and this happened, for example, when gold miners went into California and started sluicing tons of sediment into rivers in the Central Valley, or when farmers, from Europe came to Wisconsin and Minnesota and, started plowing up all the fields, ripping up the prairies, and all of that sediment ended up in the valley bottoms. The rivers aggraded by several meters. So, and when they aggraded, they became steeper in order to be able to transport the sediment that they were provided. Here are some pictures which I think might make this make a little bit more sense than that kind of balance diagram. Although I show that to you because it's a pretty classic figure in geomorphology and a good one to be familiar with. So If, for example, we have low water discharge down here or high sediment input discharge, we're going to create steep rivers because the river has to have a steep slope in order to help that water be able to have sufficient shear stress against the bed to move the sediment. If we have high water discharge or low sediment input discharge, the slope is going to be gentle because a river in equilibrium will actually be reducing that effective shear stress to reduce the sediment transport rate to be able to move that small amount of sediment that's being input with the provided water. So lots of sediment steep, lots of water gentle, little bit of water steep, or a little bit of sediment tends to create gentle slopes. And so this adjustment by changing slope is how rivers naturally respond to changes in external forcings and eventually return to being at grade. So these processes of the processes by which these rivers approach grade exist across watersheds and set the slopes and then the concavities to the overall shapes of rivers. And so what you can think of is that there is a geomorphically effective discharge, so this is typically the bank full discharge, that we consider to be important for moving sediment and shaping the channels. And so we can consider the changes in that discharge as one driver of changing river slopes. So for example, if the water discharge is increasing as we go downstream and the sediment supply is staying the same, then we might have this concave up profile. If the water supply is decreasing as we go downstream and the sediment supply is staying the same, we're going to have this convex up long profile because as we go farther downstream, the river is going to have to move more and more sediment, move the same amount of sediment with less water. There are also sediment inputs and sediment attrition. And sediment attrition is the removal of clasts by them banging up and grinding against each other and wearing down and becoming something that the river no longer is transporting as bed load. Sediment that's moving close to the bed, but it starts moving in high suspension and being whisked out of the system. So, if we have a system in which we have dramatically increasing sediment as we go downstream, or we have reducing water supply, we might expect an equilibrium shape of a graded river to be convex. If we have a system in which the two are increasing at the same rate, sediment and water supply are increasing at the same rate, or perhaps maybe sediment and water supply are just prescribed at the inlet of the river and don't really change downstream, then we might expect this long profile to be straight. And if we expect that the water supply is going to be increasing as we go downstream faster than how quickly the sediment supply increases, we might expect the river to have a concave up long profile like this. So, this case on the left is pretty uncommon. And I want to make something really clear about this. A lot of rivers that we have in the upper Midwest have long profiles that look like this, where they're starting out flat and then they're diving down, whether it's the tributaries to the upper Mississippi, to the Minnesota River, to Lake Superior, and this is just in the state of Minnesota. Many rivers look like this, but those rivers are actually have significant components that are not at grade. They're continuing to adjust right now to the deglacial related changes in the landscape. And so this sort of system set up as a graded river is not very common because it's really rare that we're going to end up in a situation where we have a ton of sediment supply farther downstream, and even more rare that the water supply is going to be decreasing downstream, right? Because as the river goes farther downstream, the drainage basin area increases. There's more catchment area that the river can draw from, and therefore the discharge is almost always increasing, the discharge of water. So in this middle case, we can consider this, I call it a flume. It's like you have a input of water and sediment at the top, and the and this panel was actually supposed to say sediment to water supply increasing downstream at the same ratio or staying constant as we go downstream. And the third option, and this is very common across the world for precipitation-fed streams, and so we have persistent water and sediment supply occurring throughout the watershed. And so the sediment to water supply ratio is decreasing downstream in this case because we have additional precipitation from more rainfall going through the catchment as you go farther downstream. But as you go farther downstream, sometimes the landscape goes from being more of an upland hilly area to a lowland area where there's less coarse sediment being supplied to the channel. And there also can be removal of clasts by attrition. And so overall the sediment supply might be increasing as you go downstream, but not quite as quickly as the water supply is increasing. So for these flume examples, there's a real flume on the left from the St. Anthony Falls lab. And so here on the lower left, we have a inlet where we were feeding water and sediment. This is my colleague Sarasavi back in 2015. And this is the channel that she's creating. And this is a figure from Steffi Tefelde's paper. She was another scientist working with us, and you can see these channel slopes are basically straight. Here's another example from a PhD student, Shanti Penprase's work. She's the TA right now as I record this, and she's working on the Rio Santa Cruz in southern Patagonia. And so this is a river where, so this lake, Lago Argentino, and glaciers used to cover the entire bed of this lake. And so this river has evolved in response to one dominant water and sediment source at the upstream end, just like this flume over here. And it's crossing a desert, so there isn't a whole lot more water supply coming in from the rest of the downstream area. And plus, the glaciers are supplying so much sediment by eroding this part of the southern Andes that any extra sediment that's added that farther downstream is pretty negligible. And so once again, we get this very straight slope. This is in contrast to these concave uprivers, which are really the archetype. So I actually just pulled a figure from the National Park Service. And this shows a kind of classic view of a river starting in the mountains, going through this transfer zone, this middle zone where there's kind of uplands and floodplains, and then eventually going into these lower reaches, this depositional zone, and eventually ending in a river delta. And here in the upper Midwest, we know that not all rivers start in mountains, but this is just kind of the classic view, right? And even if we don't have rivers starting in mountains, they still often, if precipitation fed, will follow this concave up pattern. So, considering that, let's think about what happens up here in the far upstream reaches if we have these bedrock-dominated mountain areas. So thus far, we've talked about the graded river, so this state of equilibrium at which sediment supply is balanced by the amount of sediment being transported out of a reach, and also about Lane's balance, which helps us understand how rivers will aggrade or in size in response to changes in sediment and water supply. But up here in these bedrock-dominated areas where bedrock is actively eroding, all these rivers are undersupplied in sediment, and they erode via detachment-limited rules, so they're no longer actually limited by their ability to move sediment. And as a matter of fact, they're removing sediment so quickly that they frequently scour to bedrock. And at this region of the landscape, these concepts of grade do not apply. And yet, this diagram is still showing what looks like a generally concave up river long profile pattern. And I've been saying long profile a few times, but just to remind you, the long profile or longitudinal profile is the elevation versus distance downstream on a river. So what we might wonder is, why do we keep this concave up shape? And we're going to go into that shortly when we discuss simple models for bedrock erosion.